In this section, we discuss global illumination or GI. Global illumination is a series of algorithms to make lighting in 3D renders more realistic and look closer to how light rays work in real world. Without global illumination enabled in the settings, we could only get direct lighting, the light that directly comes from a light source. But when GI is enabled, those light rays won't be killed off when they hit the first surface point on their way from the light source. Like real world, those light rays start to bounce back and forth from those surfaces, and as those light rays hit a surface, they arrive with illumination and color information from the last surface point that they hit. But with each bounce, they lose some of that energy, until using the vary settings we tell the light rays to stop bouncing. Keep what I just explained in mind. Let's go to the scene and let's see what we have. As you can see, it's a fairly simple scene and it's going to help us go through the very basics of global illumination concepts very easily. I have a vary light on the ceiling and that is our only light source in the scene. I have two cameras in the scene, and for the second one I have clipping planes enabled so we can see inside the room. Let's open up our frame buffer. In the first two render, global illumination or GI is disabled, so we are only dealing with direct lighting. And in the last two renders, GI is enabled, so we have both direct and indirect lighting. Let's select the render with GI off from our first camera. Now let's see how light rays function in real world. So first, the light rays are cast from the light source into the scene. Those light rays travel until they hit a surface, and based on how bright the light source is and how far is the surface from the light source, the surface gets illuminated. When a specific light ray hits a surface, obviously it can't continue its path and we are gonna have shadows. Right now the shadows are very dark. That is because GI is off and we won't allow our light rays to bounce back and forth between surfaces, and they get killed off as soon as they hit the first surface on their way from the light. But as I mentioned in the introduction of this lesson, in real world light rays aren't going to be killed off when they first hit a surface. They are going to bounce back between surfaces and transform information between them. When we enable GI, we allow the light rays to have this realistic behavior. Now if I load the render with GI on, we can see the shadows are a lot brighter. So let's draw some light rays here and see how this realistic behavior is happening in real world. We focus on this desk and chair here, and you can imagine the same scenario for the rest of the scene. So the light rays are cast from the light source in different directions. Obviously, some rays hit the top of the desk and top of the chair, illuminate those surfaces and cast the shadows beneath them. Now let's imagine a light ray hits the floor near the chair and the desk. Now, as we know, this ray is going to continue to bounce, and let's say in its first bounce, it's going to hit under the chair and illuminate that surface a bit. It bounces from that surface again, and based on its vector, it's going to probably hit the areas with the dark shadows beneath the chair and therefore making the shadows a bit brighter. Obviously, with each bounce, the ray is losing some of its energy. One of the fascinating things about GI is what we call color bleeding. As I mentioned, those light rays carrying both illumination information and color information. Now let's clear out these drawings. Let's say a light ray is cast from the light source and hits this red wall. We have GI on, so we expect the light to bounce and hit another surface. Now, based on the surface properties, this light ray might scatter into several rays and each one would continue to bounce in the scene. Let's say one of these rays bounces back and hit the ceiling near the wall. This ray now has some color information and has picked some red color from the wall. And when it hits the next surface, that surface is going to be a bit redder compared to before arriving this ray. If I right click here on this wall and take a look at the pixel information, we can see the red value is almost twice the green and blue values. You might ask, if this ray is having red information, why it's not turning the surface into a pure or a bit more obvious red color? Because first of all, this light ray is losing energy at each bounce, and the receiving surface has some surface properties, or might have some surface properties, that might block some of that information. Here in this render, we can see all the surfaces close to the red wall are redder, and the ones close to the green wall, or the ones facing it, are greener. In this example, we use some lonely rays to explain how light functions, but in fact for each scene we are dealing with millions of rays, and that's why the renders are often takes a very long time. Now let's close our frame buffer and go to our render settings. Obviously in V-Ray, to enable global illumination and control its settings and its parameters, you have the GI tab, and you can check enable GI to get V-Ray to calculate GI for you. For starters, let's make sure the interface is set to default. Obviously you can click on this button and change the UI to advanced or expert and reveal more options, but in this case we only need the default options. The first thing you notice is we have primary and secondary engines. Primary engine is calculating the first light bounce, and secondary engine calculates subsequent bounces. And obviously you can use different methods like irradiance map, light cache, and brute force to compute those light bounces. Now let's see how V-Ray uses these primary and secondary engines. Let me go to the second camera with GI on render. Our main camera is about here in the scene. Now, in order to determine what is in the view, V-Ray casts the first rays from the camera into the scene. When a ray hits a surface, to determine whether that point is in illumination or in shadow, a ray which is called a shadow ray, let's use a black color for this ray, will be cast towards the light source. If there is no object or obstacle between that point and the light source, that point would be in direct illumination. But if there is an obstacle between that point and the light source, that point will be in shadow. Until now, we just determined the direct illumination, whether a point is in direct light or in shadow. Now it's time to calculate GI or indirect illumination. So let me just clear these drawings. The color I'm using here are for pure presentation and have absolutely no specific meaning or role in the calculations. Now these green rays are cast from the camera, and when they hit a point on a surface, a sample will be created. That is what we call it, a GI sample. And let's imagine these samples are red. Now from this point or sample, which we already have its direct lighting information, whether it's indirect light or shadow, the first primary GI engine comes to play and sends out a hemispherical burst of rays into the scene to gather information from the scene. So if a ray hits the green wall, based on the distance between the sample and the wall, that point will get some of that green color from the wall. And if another hemispherical ray or primary ray, let's say, hits the red color on the other wall, let's say that red wall is closer to the sample point compared to the green wall, now that sample point will gather more red compared to green. That's what the primary engine does. But we said that in real world, the rays are not going to be stopped when they first hit the surface. From the second bounce, the secondary GI engine comes to play. And from each primary ray, casts or bounces another ray, and that ray, which let's say is blue, will continue to bounce in the scene and transform information between points in the scene. The secondary engine will continue to bounce the rays in the scene and will stop based on the settings in the GI tab. So we can tell the secondary GI engines to bounce each ray for, let's say, 3 times in the scene. Obviously, the more we let the rays to bounce in the scene gets brighter and the final render would be more realistic. But as with each bounce the rays lose some energy, after a while they don't have any worthy contribution to the final lighting and rendering. So we can kill them off, and by doing so our render times will be more manageable and faster. Also, the first burst of rays, which is controlled by the primary engine, we can control how many rays it will cast into the scene from each samples in the settings window, which we'll discuss in the upcoming lessons. And we will discuss all of that and all of these engines and irradiance map, light cache, brute force in this section. Just wait for it. So that was an introduction to how light functions and what is direct and indirect lighting, what is GI, and how it works in V-Ray. From the next lesson, we start learning about different GI engines that we can use as our primary or secondary GI engines. See you in the next lesson. In this lesson, we talk about brute force GI engine. Brute force is the most basic GI engine. It's straightforward, very easy to set up, and gives you the best GI solution out there. One problem though, it's very slow, and the reason being is in brute force, every shaded point, obviously in the camera view, has its GI computed separately and independently from other points. So even though it's slow, but because brute force calculates GI for each point separately, it can give you the most accurate GI solution. So let's jump in and see how it works. For the first part of this lesson, I'll be using the same scene we had for our previous lesson. Let me open up the frame buffer. Now let's see how brute force works in general. Our camera is roughly here in the scene. Brute force is a view-dependent GI method, so everything should start from the camera to determine what is in the view and what's not. So the first rays, let's say they are green, are cast from the camera. Now, because in this case brute force is handling our global illumination, every single shaded point or every pixel in the camera would get one of these rays. So if you imagine a 1000 by 1000 render, we are gonna have roughly about 1 million initial rays from the camera. Now at each point we are gonna have a GI sample, obviously. Let's say they are red. Now, from each sample, the first primary rays in a hemispherical fashion will cast into the scene and start gathering information from the scene. The number of these primary rays depends on the subdiv parameter in our brute force settings. Now, based on those information, we are going to have our GI solution for those points. So that's what brute force does if chosen as a primary engine. If selected as the secondary GI engine, from each point on the surface that was hit by a primary ray, a single ray will be traced and starts to bounce back and forth in the scene. The number of those bounces depends on the secondary bounces parameter in the brute force settings. Now let's see how brute force is going to handle our global illumination in this simple scene that we have. In the render settings window and in the GI tab, make sure to enable GI. As you can see, you can set brute force as your primary or secondary engine. In this case, let's set it as our primary engine, and for the time being, let's set the secondary engine to none. Now, without changing anything, let's render the scene. To analyze the renders a bit better, in the Render Elements tab, let's add our global illumination and our lighting passes. Now, as you can see, we start rendering the final image immediately when brute force is set as our GI engine. When we cover other GI engines, you realize that actually they go through some pre-passes to calculate GI before rendering the final image. Now let me stop the render and show you the final render. It took almost 7 minutes, even though we haven't changed anything and every setting is at its default stage. You can see it's a bit noisy, and if you compare it to the render from the previous lesson, you can see it's a bit darker, and that's because right now we are only using our primary engine and there is no secondary engine to handle our subsequent bounces. Now let's close the frame buffer and get back to the render settings. In the brute force GI rollout, you can see the subdivs parameter is grayed out. V-Ray is interrelated in almost everything, and right now we are letting our image sampler and global DMC controls, which we'll be discussing in the next section, to control almost every subdiv parameter in the scene. So basically, based on the settings in our image sampler, it decides how many samples it needs to calculate the GI solution. It's a very reliable system and almost always works. Here, because I want to actually demonstrate how this subdivs parameter works and affects your GI solution, I'm going to limit the image sampler power a bit by doing the followings. First, in the image sampler tab, set mean shading rate to 1 and turn off divide shading subdivs. In the bucket sampler rollout, enable use local subdivs. Let me set my noise threshold to 0.1, which is a ridiculously high number. Now, if I go back to the GI tab, you can see now not only the subdivs parameter is available in the brute force rollout, but now if we actually change this parameter, we can see how it works. So we said that the subdivs parameter determines the amount of primary rays, but the actual number of the rays is proportionate to the square of this number. So right now we have 8, so we expect to have about 8 by 8, 64 samples or rays. But as you can see, the number reads 16. That's because we still have some adaptivity controls that won't allow us to use all of these 64. And that particular control is adaptive amount in the global DMC rollout. If I go there and zero it out, now you can see the number actually reads 64, but it's not wise to do that, and let me set it back to 0.85 and get back to our GI tab. We'll be discussing these parameters. I mean, I'm trying to not confuse you right now. I know these parameters are really confusing right now, but at the same time, I need to touch them here and there to make sure when we actually talk about image sampling in our next section, you know how it relates to, for example, GI somehow. Now, to avoid any confusion, let me just focus on the GI tab and imagine there is no image sampler at all. So let me set the subdivs to 1 and see what would the results be in our frame buffer. As you can see, the render was very quick, about 54 seconds. Not very quick, but hey. The render is extremely noisy. As you can see, we have so many red, green, and dark pixels. And the reason is each GI sample, remember those green rays coming from the camera and making the GI samples, the red GI samples? And from those samples, we cast the primary rays, right? Those rays would go out in the scene to gather information and determine the illumination of that point of that sample, right? Now the subdiv or the subdivs parameter is set to 1. In the best case scenario, each sample only casts one ray, right? And that ray can only hit one surface. So for example, in that case of this red pixel, for example, that one ray had encountered the red wall, and because it couldn't send any more rays to gather more information from the other surfaces and average the result, we get a red pixel, right? So you can see the overall result is really noisy and unacceptable. And if I go to the global illumination pass, you can see it's quite, clear how worse it is. And the illumination also, it's not only noisy, the illumination is not going to be correct because we just don't have enough rays to go out in the scene and make that sample look correct. So the overall result, when we average all the samples together, would be a mess. Now let's get back to our render settings and set the subdivs to 2 and take a look at the result. As you can see, the result is a bit cleaner because now each point or sample can send out up to 4 rays into the scene. So 2 by 2, 4. So obviously it's a bit better, but not quite perfect. We can compare these to our previous results, and also we can take a look at the GI passes and compare them and see how cleaner it gets, which is not too much. Now let's set the subdivs to 8 and take a look at the results. As you can see, it's a lot cleaner compared to our previous results. And if I compare the GI passes, you can see we get a much better result. Now in the next render, brute force subdivs is 16, and no surprise, the result is better and less noisy. In the next render, I cranked up the subdivs number to 64, and now the result is really better. But as you can see, the render time went from 53 seconds in our previous render to 8 minutes and 30 seconds, right? And if the scene was more complex, even 64 wouldn't do anything for us, and we needed to increase that number to 128 to 156 until we get that beautiful noise-free result. Now if I go to my lighting pass, you can see some of the noise in the scene is coming from the light source that we have in the scene, so from the direct lighting. To make sure the light is giving us a clean pass, let's select the light and increase its subdivisions to 128. Now as you can see, we cleaned up the overall noise produced by the light. And we need the secondary engine to come in and start bouncing our primary rays to get more accurate GI solution. In our render setting, let's go to our secondary engine and let's select light cache. I mean, you wouldn't normally use brute force as your secondary engine, and light cache can be very quick as secondary engine and produce excellent results. So let's see, make sure brute force subdiv is 64 and light cache subdiv maybe something like 1000 would work in such a simple scene, and we'll be discussing light cache obviously in a future lesson. If we take a look at the results, now that we have a secondary engine, the render is a lot brighter and more accurate compared to our previous render. And especially if I compare the GI passes, you can see how it differs from the previous renders. And because we obviously have the secondary engine and the whole illumination gets a bit brighter, that helps us to kind of hide some of the noises also. And finally, to get rid of those aliased edges that we have, we need to increase the quality of our image sampling. Decrease the noise threshold to 0.007. And as I mentioned, it's really interrelated, and I need to kind of touch some of these parameters sometimes here and there to get the result that I want. So, and if I take a look at the render with these settings, you can see the render took up almost 45 minutes, but the render is pretty clean, right? Perfect. Now what we can is to give V-Ray some of the controls back and see how it works. So in our render settings, let's enable divide shading subdivs and increase the min shading rate to 256. I mean, 256 is a high number, and you wouldn't use possibly such a high number here. But because this scene is raw and I don't have any material, and these rays are going to be primarily used for, you know, kind of GI, to increase the quality of GI. That's why I'm using. So if you know V-Ray and you know your way around V-Ray, you know, don't accuse me of ignorance or anything for increasing this number that high. Right now I'm just having GI, no other effects, no materials. So these extra rays are going to be used with GI, and so for now, and we'll be discussing image sampling in detail in our next section. But for now, let's turn off use local subdivs and render again. The render you would get is not as clean as the previous render, but it's quite clean and acceptable, and it took only 12 minutes, which is almost 4 times faster compared to our previous render. Also, if we kind of added the denoiser that we have used in our previous section also, and we used a preset like mild on that, we could have kind of have a very clean render without that extra time. Maybe it would have been a bit softer, the overall result, and we wouldn't get as much as detail, but still it would have been amazing. Now let's explore a bit more complex situation. Now, in the next scene, we are dealing with a very detailed interior scene. As you can see, I have a V-Ray sun and sky in the scene, and also 2 skylight portals that help with the lighting, as we discussed in our previous section. The curtains have been excluded from these portal lights. Except for the curtains, all the objects in the scene have a neutral gray material applied to. And the curtains have a translucent material which allows the sunlight to enter the room. In the render settings window and under the GI tab, make sure brute force is your primary engine. Like the previous example, let's set the secondary engine to none. Our image sampler parameters are at their defaults. Also in the render elements, we have lighting and global illumination passes. Let's render the scene and see what we get. As you can see, it almost took 40 minutes to render this. The GI solution is quite accurate and we keep every detail in the render, but if I go to the GI pass, you can see it's really noisy in some areas. Now let's go back to our render settings and make sure min shading rate is 1 and divide shading subdivs is disabled. Increase the noise threshold to 0.1 and enable use local subdivs. And let's render the scene with these subdivs set to 1, 8, 16, 64 and 128, and let's see what we get. And to make it easier and quicker, I just render half of the image because it's really gonna take a very huge amount of time to render the scene when we're actually using a high subdiv number. So in the first render, brute force subdiv is set to 1, and as you can see, the final render is very noisy, and the global illumination pass is not presentable at all, and it's very inaccurate because we don't have enough rays and enough, basically enough rays to gather information for the samples in the scene, right? As we increase the subdiv to 8, we start to get more accurate GI solution, right? But it's still very noisy and dark. Make sure to check both the RGB and the GI passes here. Now, when set to 16, we don't have any noticeable improvements. It's generally a bit better, but really it's not that much better. When set to 64, now we get something significantly better, and the render time has almost doubled compared to the previous render. Now, this render is quite cleaner, but it's still noisy. When we set this to 128, we get much cleaner render, but as you can see, it's still quite noisy, even though it took almost 20 minutes to render. Now, I can go ahead and increase this to 256, but it's still gonna be some noise in there, and it's gonna take a very long time to render. Instead of increasing these subdivs again, let's enable our secondary engine and use light cache as the secondary engine. But honest to God, when you're actually trying to render an interior scene with brute force, which is not a good idea to actually render interior scenes with brute force, and I'm gonna get to that in a moment, but you really need to crank these numbers so high to get that noise out there. And it's just gonna take a very long time unless you have a very powerful network of machines to render your scenes. You're gonna be in a very bad situation. Now, in the light cache settings, set the light cache subdivs to 1500. And to reduce the overall noise, let's decrease our noise threshold to something like 0.01. So our image sampler can get rid of some of the noise produced by our GI and also some of the alias edges. Also, let's add a vary denoiser pass and set the preset to mild, so we can also have a clean pass generated by our denoiser pass. Now, if you take a look at the results, as you can see, the render is quite clean and acceptable. The GI solution is extremely accurate and keeps all the little details in the scene. But the render time, even though I just render half of the image, is more than 2 hours on this machine. Even though when I render, I almost do all the other things in the background, you know, editing the videos and browsing web and all of that stuff. But even with that, it just it takes too much. Also, if I take a look at the denoiser pass, you can see it's giving us a super clean pass, which is amazing. As it appears here, it's not a good idea to use brute force in a complex interior scene because it's very, very slow. I even didn't dare to render the entire scene because I knew it would take a very, very long time to finish. To wrap up this lesson, let's summarize the strengths and weaknesses of brute force GI method. For its strengths, we can say that it preserves all the details. You can see there wouldn't be any artifacts or flickering in the animation if you use brute force as your GI solution when you are rendering an animation. It doesn't require tons of RAM, so if you don't have enough RAM on your machine, you can simply and safely use brute force to handle your GI. And as its weaknesses, we can say it's very slow, unfortunately, and especially for interior scene. It's really hard to clean it up, and there would be noise to some extent in the final render, even if you use a high amount of subdivision, which is not a good thing. Perfect. So that's about brute force, and in the next lesson we'll be discussing irradiance map. In this lesson we talk about irradiance map, and we'll see how it works in theory, and we'll try to create a GI solution for our simple and complex scenes. And finally we'll see what are its strengths and weaknesses. Get ready for a very long lesson. The key difference between irradiance map and brute force is the fact that in irradiance map, instead of computing GI for all the shaded points that are visible to the camera, GI will only be computed at some points and interpolated for others. Let's open up our render settings, enable GI, and set irradiance map as your primary engine, and set the secondary engine to none. And as you can see, there is no irradiance map in the secondary engines. That's because it only can be used as the primary engine. Let's open up our frame buffer and see how irradiance map works. Let me hide the history panel and have my render settings window also open besides the frame buffer. The camera is roughly here in the scene. As it is a view-dependent method, the first rays are shot from the camera into the scene to determine the placement of the GI samples. Now, remember, unlike brute force, we wouldn't have one sample at each shaded point or at each pixel. The samples will be created for only some points in the scene. Pay a very close attention to these terms that I'm using, because unless you really want to understand how irradiance map works and how those parameters are going to help you come to a better GI solution, you really need to focus and pay attention. Okay. So when one of these rays hits a surface, a GI sample will be created. From these points, the hemispherical burst of GI rays will be traced into the scene to gather information. And the number of these rays is controlled by the subdiv, or in previous versions of V-ray, hemispherical subdivision parameter. Obviously, more rays equals to a higher quality GI solution. So when you increase this number, you're going to get a higher quality GI solution. The quality of samples are going to get increased. Okay, now that we have the GI solution for some of the points in the scene, what about the points that weren't lucky enough to get any GI samples? Now, for those points, V-ray takes some of the already calculated samples from around that point and interpolates between them and averages them out to come out to a solution for that point. And the same thing will happen for the other unsampled points in the scene. And like before, if we have a secondary GI engine enabled, when a GI ray hits a surface, the secondary engine tries to bounce that ray in the scene. One essential thing you need to know about irradiance map is that it's produced in several passes. What I mean by that is, let's say in the first pass, the samples are created all over the place in a random fashion. In that first pass, irradiance map tries to assess the scene and see where are the details in the scene. In the next passes, in each pass, it tries to add more samples to more detailed and more complex parts of the scene. We will visualize that in a few moments. Now, let me close my frame buffer and get back to the render settings. Now in the render setting and in the V-ray tab, let's turn on use local subdivs. I won't mess around with image sampler settings just to avoid any confusion here. Okay. In the global switches rollouts, make sure don't render final image is disabled. If this is enabled, only the GI will be calculated and V-ray wouldn't render the final image. Also in the render elements tab, I have global illumination and lighting passes. Also, I'm going to select my light and increase its subdivision to 64 so we wouldn't get any noticeable noise from our direct lighting. In the GI tab and irradiance map rollouts, make sure the interface is set to expert by clicking on this button twice. And let me set my current preset to medium and take a render and see what we get without changing anything else. I mentioned that irradiance map is created in several passes. Now based on our settings, we are using 3 passes to generate irradiance map. We can decrease or increase the number of these passes very simply. In the first pass, it tries to get an idea of the scene, and in the following passes, it adds more and more samples to the detailed areas. And after these passes are calculated, we start to render our final image. This is our first render, and as you can see, it took about a minute, which is very quick, and we have a fairly clean GI solution. And if I go to the GI pass, you can see it's clean, even though it might lack some details compared to a brute force. These noises are actually coming from the light, but to increase the speed of these renders, I didn't increase the light subdivisions that much, so these noises are coming from our direct lighting. Now let's close our frame buffer and start explaining irradiance map parameters. The first parameter is current preset dropdown. We have custom, very low, low, medium, medium animation, high, high animation, and very high. So obviously when you go from very low to very high preset, you are going to increase the overall quality of your irradiance map and also increase your render time. Each of these presets contain predefined settings for some of the irradiance map parameters, which are min and max rate, and color, noise, and distance thresholds down here. Right now we don't have any idea what these parameters are doing, so let's set this preset to custom so we can adjust these parameters as we wish. The first and most important irradiance map parameters are min rate and max rate. Remember, we mentioned irradiance map is created in several passes, and each pass adds more samples to the more detailed areas. Not only we can control the number of these passes using min rate and max rate, but we can also control the resolution at which those GI passes are being calculated. Right now, min rate is set to -3 and max rate is set to -1. That means we have 3 passes, -3, -2, and -1. If I change my min rate to -4, now we are going to have 4 passes, -4, -3, -2, and -1. And if, let's say, max rate is set to 1, now we will be having 6 passes, -4, 3, 2, 1, 0, and +1. And with each pass, we'll add more samples to the detailed areas. Now let's set the min rate to -3 and max rate to 0. Min rate determines the resolution of the first GI pass, the one with the least amount of detail. If min rate set to 0, this pass would have the same resolution of the final image that you are having. If set to -1, it would have half of the final image and half of the final image resolution, and so on. So when set to something like -3, we are using a very low resolution to calculate the first GI pass, and this pass would be good enough for large, flat, even areas. And as we go through the other passes, we increase the resolution twice each time and add more samples to the detailed areas. And max rate determines the resolution of the final GI pass. Now let's see that in action. Make sure show calculation phase is enabled so we can see these passes. And also let's change the preview from full preview to show new samples in green. Now in this preview mode, each pass adds new samples in the detailed areas, and we only see those new samples in each pass. Now when we will render, you notice that in the first pass the samples are very random, and with each new pass we focus more on detailed areas. In this case, let's set the max rate to 0 and open up our frame buffer, and let me clear the current render and start a render. Now the first pass is very quick and we randomly generate some samples in the camera view. In the second pass, which is twice the resolution of our previous pass, we only add more samples to the corners and smaller details. And in the third pass, we even pay more attention to those more detailed areas. And in the final pass, we barely add any samples to any flat areas and pay even more attention to the corners and complex intersections. On the red wall, those green samples are shown as black, but it's just a preview and doesn't matter that much. So clearly, if you use a min rate of, let's say, 0 and max rate of 3, you're going to also have 4 passes. but those 4 passes are going to be having higher quality compared to, let's say, -3 and 0, sorry. So they would take more time to calculate, and at 1, when we're using the pass 1, for example, we are going to have double the resolution of the final image. But the right thing to do is to always set the mean rate as a negative value so we can calculate less interesting and more flat, even areas very quickly. So the higher resolution passes would be used to calculate more complex areas. In the V-Ray tab and global switches rollouts, let's make sure don't render final image is inactive. Now I have 2 renders to show you, one with the mean and max rate set to -7 and -4, and the other one with mean and max rate set to -3 and 0. In the lower quality renders, you can see tons of details are gone. Take a look at these legs down here, and if you compare it to our higher quality render, you can see the contact shadows are almost gone, and you can see that throughout the scene if you pay close attention. And you can also see some artifacts here and there. Now let's get back to our render settings. Next we have subdivs, which controls the number of primary GI rays. So the higher this number, the higher the quality of our GI samples. Let's render our scene with different subdivs number and see what we get. In the first render, subdivs was set to 1, and as you can see, we have an extremely splotchy render. That's because each sample can send only 1 ray, and the quality of those samples are going to be very low, and they are going to be very inaccurate. Now in the second render, the subdivs was set to 4. So each sample can have up to 16 rays, and obviously the quality is a lot better compared to our previous render. In the next render, the subdiv was set to 10, and obviously the quality is a lot better. And you can also check out the GI passes and the RGB passes to see how they differ. Next we have 50. So we basically have a clean render. Now each sample can send out up to 2,500 rays into the scene. The averaging of all of those information is going to result in a much more accurate result compared to our previous renders. Now for such a simple scene, 50 would possibly be more than enough, but in more complex scenes we can increase these numbers, and in this case I have this render with the subdiv set to 200 here. As we increase the subdivs number, you notice the render time is also increasing. So basically calculating the irradiance map passes are going to take longer because the samples sending a lot more rays as we increase the subdivs number, but also the quality is getting better. Next we have interpolation samples, which is the number of samples to interpolate the global illumination at a given point. You remember when I said that in irradiance map GI will be calculated only for some points. For those points without any GI samples, the GI will be calculated by interpolating and averaging the neighboring samples. Now the number of those samples is controlled by interpolation samples number, or interpolated samples number. To see how it works a bit better, let's decrease the subdiv number to 4 and render a few images with different interpolation samples. In the first render, the interpolation sample is set to 1, and as you can see, it's very blotchy. In the next render, it was set to 4, and we get blurrier results compared to the previous one because now we are using more samples to interpolate a given point. As I increase this value to 10, 20, and 80, you can see each time we get less splotchiness more blurriness and less detail in the scene. Next, I increased the subdivs to 50 and repeated the same process. Now, the individual samples are having a higher quality solution and they are more accurate. As we use lower interpolation values, the result is splotchy with more detail, and as we increase it, the result gets blurrier and less detailed. For example, if I compare the renders with interpolation set to 20 and 80, you can see in the 80 version we lose tons of details and contact shadows compared to the when the interpolation samples was 20. So as you can see, neither the low values nor the high values represent quality. You need to stay in between, and maybe something like 20 to 35 is an accepted range to be used as your interpolation sample. But really generally depends on the scene, and as you can see, we can use very high number like 200 to solve some complex scenes. Now we're going to be discussing that later on in this lesson. Now let's set the interpolation samples to 20 and continue with the rest of our parameters. The next option is use camera pass. If you have an animated camera in your scene and you want to calculate the irradiance map for the entire camera pass in one go, you can turn this option on. So whether a fly-through animation or an animation with moving objects can benefit from turning this option on, and it helps to reduce flickering in your animation. We will be discussing how to deal with rendering animations later on in this course, but for now I think this simple explanation will be enough. Next we have interpolated or interpolation frames. As you can see, this option is grayed out and only works when the irradiance mode is set to animation. And as the name of this mode suggests, it can be used to render animations. We will discuss it later on. Now, the interpolation frames number controls the number of adjacent frames to the current frame that their irradiance map will be interpolated to smooth out the final result and remove any possible flickering. So right now the interp frames is set to 2. So if we are, for example, rendering frame 10 in the animation, the irradiance map for frame 10 and 2 frames before that frame that are 8 and 9 and 2 frames after it, which are 11 and 12, will be interpolated. So in general, 5 frames will be interpolated when the value is set to 2. Also, the number of interpolation samples depends on this parameter. Right now, 5 frames will be interpolated, so the interpolation samples will be multiplied by this number. So the overall interpolation samples would be 100 to further smooth out the final result. If you want, you can, reduce the interpolation samples in that situation. Now we'll be talking about this parameter later on, and I know it's confusing right now for you, but in the final part of this lesson, when we are actually talking about the irradiance map modes, you will see kind of how this parameter relate to the animation modes in the modes down below. Now let me for now set the irradiance modes back to single frame. Next we have show calculation phase, and as you know, if enabled, it will show you the irradiance map passes, and in this drop down you can decide how the samples are going to show in the irradiance map calculation. Let me set these to full preview for now. Next we have show samples, and if enabled, the irradiance map samples are actually going to show up in the final render. Let me show you a render with this option enabled. Now you can see all the GI samples that was added to the scene in different irradiance map passes. Then there is show direct light. It will show direct lighting for primary bounces in addition to indirect lighting while the irradiance map is being calculated. Generally, you really don't need to touch this option at all. Next we have color threshold, normal threshold, and distance threshold. Color threshold controls the sensitivity of irradiance map to indirect lighting. Distance threshold controls the sensitivity of irradiance map to distance between surfaces, and normal threshold controls the sensitivity of irradiance map to surface normals. For color and normal thresholds, the smaller the value, the more sensitive irradiance map will be, and therefore the final GI solution will be more accurate and detailed. But for distance threshold, higher values means more samples where the surfaces are close to each other. That's why as I change the preset from very low to very high, you notice the values for color and normal thresholds are getting smaller and distance threshold is getting bigger each time. Now let's change the preset to medium and then to custom and set the max rate to 0. We still have show samples turned on, which is going to be very helpful in visualizing how these threshold parameters are working. In the first render, the color, normal, and distance thresholds were set to 5, 5, and 0 respectively. And if you take a look at the render, you can see even though the max rate is set to 0 and we expect to have tons of samples in complex intersections, but as you can see, the algorithm does not pay any special attention to those areas and the samples are evenly distributed because the algorithm is not that sensitive based on the parameters that we have set in our color, normal, and distance threshold. In the next render, the thresholds are set to 1, 1, and 0, and we don't see much of an improvement compared to our previous renders because these numbers are still pretty huge. In the next one, thresholds were set to 0.5, 0.5, and 0.1. Now, as you can see, we get a lot more samples in those corners and intersections and detailed areas. And in the next render, the thresholds were set to 0.2, 0.1, and 0.3. And as you can see now, because V-Ray is a lot more sensitive, we get a lot more samples in those complex areas. Now let's make sure our color threshold is set to 0.4, normal is set to 0.2, and distance is set to 0.1. Now next we have detail enhancement group of parameters, and it's very useful. If you enable detail enhancement, you can use irradiance map to handle the GI solution for flatter and simpler areas, and you can use brute force method to calculate GI in more detailed areas of the scene. When you use detail enhancement, you can utilize lower irradiance map settings because irradiance map will only be used for even and simple parts of the scene. In this case, let's change our preset to very low and we can increase our interpolation samples to something like 50, as all the detailed areas of the scene will be calculated using brute force. Also, let's make sure show samples is off. Now let me show you two renders with and without detail enhancement. In the first render, detail enhancement is off, and as you can see, we don't get to keep any details in the scene, especially with the high interpolation samples number that we have. We smooth out every detail. Now the contact shadows are almost gone, and you can go throughout the scene and see this lack of details everywhere. In the next render, detail enhancement is enabled, and even though the render took almost twice as our previous render, we get all the details and contact shadows back. Now let me zoom in some areas and compare this render with our previous one. Also, if I select the GI pass, these differences are becoming very obvious. As you can see in our detail enhancement version, all the details are back, but now the noise problem that we had with brute force is back again. So let's see what we can do with it. To control the quality of the detail enhanced areas, we have subdivision multiplier, and it is a percentage of the irradiance map subdivision. So right now our irradiance map subdiv is 50, and if I set the subdiv multiplier to 1, we're going to get all of those rays for the brute force calculations. And if set to, let's say, 0.5, we only use 50% of our irradiance map subdivision. Let's set it to 1 and maybe 5 and take a look at the resulting render. When set to 1, especially if we are in the global illumination pass, you can see not much of an improvement, but when set to 5, it's a lot cleaner, and we can clean the rest using our image sampler, but obviously the render time has increased. Next we have radius, which controls the radius for the enhancement effect. Then we have scale, which is the unit for the radius parameter. Scale is in pixel and world is in the world units. Turn off detail enhancement for now. And let me set the interpolation samples back to 20 and set the preset to custom and set the min rate to -3 and max rate to 0, and make sure the thresholds are set to 0.4, 0.2 and 0.1. Next we have randomized sample, which is on by default, and it jitters the samples randomly to prevent artifacts in the GI solution. First, let me enable show samples, and I can show you two renders with and without this option checked. When is off, you can see the samples are distributed in a grid on the scene, and when is on, the distribution is random, and normally this option should be on. Let's also disable show samples for now. Next we have multipass, and this is what gives us the ability to calculate irradiance map in several passes. If disabled, the map will be calculated in one pass, and the resolution of which is specified by the max rate, and it's also a good idea to have this option on all the time. Then there is sample visibility, and it can be really helpful to prevent artifacts like light leak through thin objects. When the two sides of that surface are having a very different illumination. Now let's visualize that quickly. Let me create a small plane object. Rotate it 90 degrees and put it in front of the scene besides this shelf maybe. Now let's create a V-Ray plane light and put it behind our plane. And let me also rotate it towards the bottom of the plane. Make sure its dimensions is about 10 centimeters and set its multiplier to something like 400, and maybe a bluish color here would work. Also, to see the problem a bit better, let's change the preset to low and set the interpolation samples to 100. Now, let me show you two renders with and without check sample visibility on. Now, the placement of the light and the plane might be a bit different compared to this render, but it would be enough to prove the point. In the first render, check sample visibility as off, and as you can see, the light on the other side of the plane clearly leaks and affects where it's not supposed to. And the reason being is that the interpolation point in that leaky area is using bright samples from the other side of the plane. But in the next render, when check sample visibility is on, that point is only using samples that are visible to it, so the artifact is gone and we are having an accurate render. Also, as having this option on adds another layer of calculation and complexity, the render time has increased considerably compared to our previous render. In most cases, if you are having fairly decent irradiance map settings, you wouldn't need check sample visibility to be on, and irradiance map would have done a nice job of preventing those light leaks. So for the next render, let's set the current preset to medium, then set it back to custom and change the max rate to 0. Let me set the interpolation samples back to 20 and make sure check sample visibility is off. If we render the scene, as you can see, we do not have any light leaks because the quality of our irradiance map is decent enough, so we wouldn't need check sample visibility to be turned on. Okay, now let me delete this plane and the light, as we don't need them anymore. Next we have calc samples. This value shows the number of already calculated samples to guide the sampling process. Values between 10 to 25 usually works. Lower values speed up the rendering, but the final solution might not be quite accurate, and higher values make the sampling more accurate, but the render will be slower. And that was me quoting the V-Ray guide. Next we have interpolation type, and obviously from the name it appears that it relates to the interpolation samples value. Here you can choose the method for interpolating samples. The default is least square feet. First you have weighted average, which is simple and fast but normally causes blotchiness in the final solution. Least square feet, which is the default method. It's better than the previous one, but it's slower. The next one is the lone triangulation, and I hope it is the right pronunciation. And unlike the other ones that try to smooth the overall result, this tries to preserve the details, and the final results might look noisier compared to the other ones. And you would need to increase your irradiance map subdivs to get a noise-free render when using the lone triangulation as your interpolation method. Finally, we have least square with Varani weight, which is a modification of the least square fit method, and it tries to improve upon it, but up to now it hasn't been so successful, and you're better off using the least square feet method. Now, the two preferred methods here are least square feet and the lone triangulation. Least square feet is great for simpler scenes and the result will be smoother, and the triangulation method is suited for more complex and detailed scenes because it preserves the details and wouldn't smooth out the final results. But to get a noise-free render with this method, you would need high irradiance map settings. Let me change the preset to very low. Decrease the subdivisions to 10. Now let me show you two renders with the interpolation method set to least square feet and the lone triangulation. Obviously, as I compared the two, you can see least square feet is smoothing out the results, and triangulation is preserving the details, and everything is sharp, but not quite in a good way. Okay, let's change the preset to medium and set the subdivs back to 50. Next we have sample lookup, and if I quote the V-Ray guide, it is the method of choosing suitable points from the irradiance map to be used as basis for the interpolation. And you really don't need to know how this works, and as you can see, there is a useful description for each of these methods from draft to fast, good, and best, and the default one, which is density based, is your best bet to get high quality renders. Next we have irradiance map modes. The first one is single frame, and in this mode one irradiance map is calculated for the whole image and for each frame. The next one is the bucket mode, and in this mode if I render the image, a separate interpolation map will be used for each of these buckets. Okay, we can stop the render. Another one that we have is from file. You provide an irradiance map file, and V-Ray won't calculate irradiance map again and uses that supplied map instead. Let me show you how it works quickly. So let me change the mode to the single frame. Click on this reset button to clear any existing irradiance map in the memory and say yes. Also, as we only need to save the irradiance map file, we can go to the V-Ray tab, and from the global switches rollout, enable don't render final image. Now you can render the scene. Now V-Ray is calculating irradiance map, and as soon as it's finished calculating, it just won't render the final image. Now we have this irradiance map file in the memory, and what we can do is save it on our disk, and let me save it in the render output folder of this lesson, and let's name it IR map or whatever you want. Now we can change the mode to from file and load the irradiance map that we just saved. In the V-Ray tab, make sure to disable don't render final image. And now if you render the scene, you notice that V-Ray skips calculating irradiance map and uses that supplied file and renders the final image immediately. Now the next one is multi-frame incremental. Before explaining this, let me quickly create a quick fly-through animation on my first camera. So let me close my frame buffer and render settings window. Make sure you are viewing the scene through the first camera. Select that camera in the Scene Explorer. Now let me enable auto key. Go to the final frame and move the camera as you wish. Now we can disable auto key. Now if I move through the timeline, we'll have this simple fly-through animation. I have 50 frames, and as you can see, the motion isn't very complex. So for example, if I compare frame 1 and 5, you can see the camera barely moves. So we don't need to calculate a new irradiance map for each frame. Using multi-frame incremental mode, V-Ray will calculate a complete irradiance map in the first frame, and from the next frame, V-Ray uses that first irradiance map as a base and adds to the map where there isn't enough detail. In our example, we can go ahead and render all the frames using multi-frame incremental, and only the first frame will get the complete irradiance map calculated, and the other frames will use that map as a base and refine that map where needs be. Now, in this case, because the motion isn't extreme, we can go and render, for example, every 5th frame, and in general, we will render 10 frames, right? Because we have 50 frames in general. Now, and the resulting irradiance map will have enough information that makes it possible to render any frame in the animation without having to calculate irradiance map for that particular frame separately. Let's practice what we just learned. Open up the render settings and make sure the mode is set to multi-frame incremental. Let me reset the existing map here. In the Common tab, enable Active Time Segment and set the every nth frame to 5. Now we are rendering only every 5th frame. In the V-Ray tab, enable Don't Render Final Image. Now if I press render, you can see for the first frame the irradiance map is calculated in full, and for other frames we'll use the map from this frame as our base. And because the other frames are only refining the existing map, they calculated the irradiance map a lot quicker compared to our first frame. I think it took about a minute to calculate the irradiance map for all of those frames. Now I can go ahead to my render settings and save the map that we just created. We just created one map, not 10 map, so we just have one irradiance map, but the resulting map is a combination of the irradiance map in all of those frames, each frame refining the previous frame and add a bit more detail where needs be. Now I can go ahead to my render settings and save the map that we just created. Let's name it maybe IR map, multi-frame, incremental, and save it out. Now we can change the mode to from file and load the map that we just saved, and as you can see, the file is a lot bigger compared to the previous file. Now I can go ahead to any frame in the scene, let's say 25 for example, disable don't render final image, and in the comment tab change the time output to single and render the image. And as you can see, we have a correct final image. Next we have add to current map. It's like multi-frame incremental, but in this mode an entirely new map will be created at each frame and add those new data, that new map, to the resulting map of the previous frame. So if I activate my third camera and select it in the Explorer, you can see we have 4 camera views in our first 4 frames. Now imagine I want to have a detailed high-res render from each of these views. So I can change the mode to add to current map, and in the comment tab render only the first 4 frames, right? Like the previous example, I can enable don't render final image and render the scene. Now the first frame is like before, a full irradiance map will be created. In the second frame, a new map based on that new view will be created, and the map will be added to the map from the previous frame, right? We're just not refining the map like multi-frame incremental, we are creating an entirely new map for each frame and add the map that was created in that frame to the map that was created in the previous frame. So we combine those 2 maps in the first 2 frames. And after 4 frames are finished, we'll have an irradiance map that is going to be perfect if we use it to render any of those 4 frames or all of them. So you just need to save the map after the render is finished, change the mode to from file, disable don't render final image, and start rendering any of the views that you want. So the next one is incremental add to current map. In this mode, V-Ray uses whatever irradiance map left in the memory and refine that from the first frame instead of calculating a completely new map from the first frame. Now the last 2 ones are animation pre-pass and animation rendering. Now when you have object animation in your scene, you need to use this mode. So if you are trying to render animation with object animation, you first need to change the mode to animation pre-pass. In this mode, one separate irradiance map will be saved for each frame. So V-Ray asks you where to ask those irradiance map for this animation. In this case, we have 50 frames, so 50 separate irradiance map will be saved and later reused. So you save it wherever you want and start rendering the entire timeline. And in this case, V-Ray is smart enough to only calculate the irradiance maps and won't render the final image. After all of those frames are calculated and the irradiance map being saved, you can change the mode to animation rendering, and using this browse button, define the files that you just saved and start rendering the final animation. And for each frame, V-Ray automatically will use its corresponding irradiance map without having to calculate it again. And if you remember when discussing interp frames up here, we said that V-Ray will combine irradiance maps from adjacent frames when rendering a specific frame. So if we render frames 23, for example, V-Ray takes the irradiance map for that frame and also takes irradiance maps from 2 frames before and after that frame. 2 frame because the interp frame is set to 2, and start blending and averaging those frames together, so 5 in general, to create a smooth flicker-free solution. We'll be discussing animation rendering in V-Ray later on, but I think it's enough for now. Let's get back to the single frame mode. Next we have don't delete option, and if you have it checked, after you finish your render, the irradiance map from that render will stock in the memory, and if you disable it, it will be removed after the render. Then there is autosave. If enabled, you can specify a location, and each time a render is finished, that map will be automatically saved on your disk in the specified location. And finally, there is switch to saved map, and if enabled, V-Ray will automatically change mode to from file and uses the map that was just saved using the autosave. Okay, so that's about irradiance map. Finally, let's just get back to our complex scene and let's see how we can utilize irradiance map method in that complex situation. Now, this is the same scene that we had when we were working with brute force. And also the scene has neutral gray material applied to all the surfaces, which makes coming up with a solution a lot harder compared to a normal textured scene. The noise and splotchiness from the GI will be much more obvious in this scene. Let's open up our render settings and see what we have. As you can see in the V-Ray tab, almost everything is set to default. I've only disabled divide shading rate subdivs. In the GI tab, let's set the primary engine to irradiance map and secondary engine to none. In the irradiance map settings, let's set the preset to medium and see what we get. If you remember, the medium preset was giving us a pretty clean solution in our simple scene. But here we are dealing with extremely difficult situation where the direct lighting has a hard time entering the room and we have so many small details in the scene. Let's open up our frame buffer and let's see the render that we are gonna get. In your frame buffer, make sure display colors in sRGB space is enabled as you check out the renders. As you can see, the final render is extremely splotchy and we haven't kept so much detail. Also, if I go to the global illumination pass, we can see the real depth of our problem. Wow, it's really scary. Now let's think about the solution here. First, I'm going to draw a small region in my render so we can work a bit faster. And this is a normal workflow for me. Instead of rendering the entire image all the time, I work on small regions, and when I'm sure everything is okay, then I render the final image. Let me just arrange these windows so we have both our render settings and our frame buffer. First, let's throw in more samples by changing the preset from medium to high and render the scene. As you can see, it hasn't quite improved anything really. Now let's change the preset back to medium and increase the quality of our samples by increasing the subdivs to 100 and render the scene. As you can see, the quality has improved, especially in the flatter areas, but we still get those splotches and artifacts in the details. Now what I can do is to increase the interpolation samples to 35 in order to smooth out those splotches a bit. Now let's render again and see what you're going to get. It's better, but we still have those splotches even though less visible, and we lost tons of details and contact shadows. For most scenes, these settings would give a beautiful render. Maybe interpolation samples is a bit too much, but in this extremely difficult scene, just increasing the irradiance map settings wouldn't be enough to get a final result. In this case, I decided to utilize detail enhancement. So as we learned, when using detail enhancement, we can use very low irradiance map settings because it's only going to be used for simpler parts of the scene. So let's change the current preset to low, increase the interpolation samples to 200, or even 150, 200 would work in this case. Enable detail enhancement, and in this case, let's set the radius to 40 pixels. Also, let's set subdiv multiplier to 1, and let's render the scene. Now, as you can see, those splotches are gone. We have a faster render, but now we have lots of high frequency noise. To get rid of these, let's increase the subdiv multiplier to 3 and render again. Now, it's a lot better, and in the RG pass, it's very hard to notice any noise. If I render the entire image with these settings, you can see the final render is pretty clean. I can check out the GI pass, and as you can see, we have barely any noticeable noise, but it took more than 1 hour to render this, which is a lot faster compared to, for example, brute force, and it's a lot cleaner compared to it. Now, obviously, we are gonna need a secondary engine to have a profound GI solution, so let's use Light Cache as our secondary engine and set the subdivs to 1500s. Also, in the render elements, let's add a V-Ray denoiser, and you can, set the preset to mild, or, it's really up to you. But in this case, I just let it to be default. Now, this is the RGB pass, and as you can see, it's very clean. Also, even though I've increased the resolution of this render compared to our previous render, and I've also added the light cache as our secondary engine, as you can see, the render time has decreased compared to our previous render because the scene is brighter, the more light is in the scene, and that's why we are getting actually a faster render compared to our previous render. And this is our GI pass, and if you compare it to our first render, you can see it's a lot better. And this is our denoiser pass, and it's getting rid of any remaining high frequency noise in the render. Now, there you have it. Finally, we can enable color correction and maybe enable white balance and use something like 7500 to add a bit warmth to the render. Let's also enable the curves and add a bit more contrast. Also, another helpful tip here when you load these history renders in your frame buffer, which I have provided with the project files of this course, you can right click on any of them, and if you select load render settings, the settings that was used to achieve that particular render will be loaded in your V-Ray settings. Now let's quickly sum up the strengths and weaknesses of irradiance map. For its strengths, first of all, it's faster compared to brute force. Then you have the ability to mix between irradiance map and brute force by having detail enhancement option, which is a big plus for me. Another big one for me is the ability to save and reuse and refine irradiance maps. And for its weaknesses, first, we can lose some detail when using irradiance map. If used for animation, there might be artifacts and flickering. Also, it needs more RAM and resources compared to brute force. So that's about irradiance map. A very, very long lesson, but I will see you in the next lesson. Hopefully you learned something. In this lesson, we discuss light cache and we'll see how it works. The first thing you need to know about light cache is that it's not quite good at picking out details, and unlike Iridian's map and brute force that are more suitable as the primary GI engines, light cache is quite the opposite and it's more suitable to be used as the secondary GI engines. So in most cases, you use Iridian's map or brute force as your primary engine, and light cache is almost always the preferred choice as the secondary engine. Now let's quickly see how it works. We are in the same simple scene that we use for explaining brute force and Iridian's map. So let me open up my frame buffer and see how light cache works in theory, which is a bit different compared to the overall way that Iridian's map and brute force works. Also, in the render settings windows and in the GI tab, let's enable GI and set light cache as our primary GI engine, and that is for pure explanation, and you would rarely, for some very specific reasons, might use light cache as your primary engine, and as I mentioned, its favorite position is secondary engine. Let's set the secondary engine to none for now. Open up the light cache rollout and make sure the interface is set to expert so we can see all the parameters. Our camera is here in the scene. As light cache is a view dependent method, first tons of rays are sent out from the camera into the scene. The number of these rays is the square of light cache subdivs parameter. Now, in this case, the subdivs is 1,000, so the overall ray count will be about 1,000,000 for this scene. So whenever these rays hit a point on the surface, they create a light cache sample, and each ray will continue to bounce in the scene, and whenever they hit, they create a light cache sample. Each of these rays that come and bounce in the scene store all of that information in their path, and as we learned earlier in this section, these rays carry information between surfaces, and this is how light cache can give us our global illumination solution. Now, to speed up the calculation, imagine a ray comes and creates a light cache sample in a specific point. Now, if another ray comes and hits that exact same point, that ray will be killed off and the information from the existing sample will be used. The number of the bounces will be conveniently controlled by a parameter called bounces. Right now it's set to 100, so each ray can bounce up to 100 times, but obviously most rays wouldn't need that much bounce. You can go ahead and check out the previous lessons and see how light cache compares to other GI solutions in the way they work. Now let's start discussing light cache parameters. Let's render the scene and see what we get with the default parameters. As I start the render, we can see a preview of light cache calculation, and depending on your settings, it might be very quick or it might be slow. The first parameter is subdivs, and as I mentioned, this controls the number of rays that are cast from the camera. Obviously, the higher the number, the higher the quality of your samples, and therefore the higher the quality of your renders. Now let's take a look at a few renders with different subdivs number. Remember, our goal here and in light cache is not to have a detailed noise-free solution. That is not what light cache is for. We get all the details we want from our Iridian's map or brute force as our primary engine, and light cache is only for secondary purposes. So as I go through the renders from subdivs of 10 to 4,000, you can see each time we are increasing the overall quality of our light cache, and at the same time increasing our render time. Okay, now let me set the subdivs to 1500. Next, we have sample size, which controls the size of the light cache samples. The smaller this value, the more accurate and detailed the GI will be, but it also will be a bit noisier. Also, you would need more RAM when the samples are smaller. In the frame buffer, you can see how as I increase the sample size from 0.01 to 0.5, each time we get less detailed subdivision and less noise at the same time. Also, you can clearly see the individual samples as their size gets bigger. Now, let's make sure the sample size is set to its default of 0.01. Next, we have scale, which controls the unit for sample size. And down here, if I change the filter type to fixed, also it controls filter size. Now we have screen and world. In screen space, the sample size is a fraction of the final image. So if sample size is set to 0.01, the sample size would be 1% of the final image, and so on. The screen unit is better for still images and animations, especially with object animations. And world unit is better for fly-through animations where only the camera works and the camera moves. Also, in this mode, the samples that are closer to the camera will appear smoother because they will be sampled more often. Generally, screen is the one you use in most cases, but if you are working with fly-through animations and you are using fly-through mode down here from the light cache modes, you can probably use world. Now, as we have been working in the screen space, you have seen the distribution of the samples in this space. Now let me change this scale to world space and show you a few renders with different sample sizes. As I increase the sample size from 0.001 centimeters to 20 centimeters, you can see the difference in sample distribution and sample sizes. Okay. Let's set the scale to screen and sample size to 0.01. Next, we have retrace and retrace threshold. When retracing is enabled, the GI for the corners and more detailed areas will be recomputed or retraced to make the solution more accurate and avoid any flickering artifacts or light leaks. And we have used for glossy rays enabled down here. Having retrace enabled will prevent any light cache artifacts in the glossy or blurred surfaces, which we'll be talking in a moment. And the value or the retrace threshold here is the amount of retracing. Usually 2 is enough for stills and 8 for animations. I have this plane and light group, and it contains a simple plane and a bright viral light behind it. Let me unhide them and turn the light on. Now you can take a look at 2 renders, one without retracing and the next one with retracing. In the first one, retrace is off, and we can clearly notice the light leak underneath the plane, and the samples from both sides of the plane are blending and causing this light leak. In the next one, retrace is on, and the light leak is basically, as you can see, gone. We can still see some samples from the other sides, but if we use light cache as our secondary engine and use let's say irradiance map as our primary engine, those samples won't be visible in the final solution at all. So let me quickly set the irradiance map as my primary engine and light cache as my secondary engine. In the irradiance map, set the preset to medium and make sure that check sample visibility is on. And in the light cache, make sure retrace is on. And this would be the render with these current settings. And as you can see, we don't have those very bright samples visible in the final render. Let's set our primary engine to light cache and secondary engine to none. Another useful option to avoid any light leak is leak prevention down here, and by default is set to 0.8. This option kind of works hand in hand with the retrace option, and let me show you 2 renders with light leak prevention set to 0 and 1, and in both of them we have retrace turned on. In the render with the leak prevention set to 0, as we can see, we get the light leak even though we have retrace on. And in the render with prevention set to 1, the light leak is gone. Now let's make sure the leak prevention is set to default of 0.08. Also, let me turn off the second light and hide the plane and the light group. Next, we have show calculation phase. When enabled, you can see a light cache preview while it's being computed before the final image being rendered. We have use camera path, and when enabled, the light cache will be calculated for the entire camera path instead of just the current camera view. In the light cache modes down here, we have a mode called fly through. If we just have camera animation and no object animation, you would use fly through mode. But if you have also object animations, in that case, the mode down here need to be set to single frame. So for each frame, we'll be calculating a new light cache, right? And in that situation, having use camera path on will reduce flickering in general, because the position of light cache samples on static geometries, the geometries without any animation, will be fixed during the animation. I have this animated cubes in the scene. Let me go ahead and unhide them. Also select the first physical camera and make sure it's the active one. As you can see, it has a simple camera animation, and also you can see these animated cubes and their dynamic motion. Now in the render settings, make sure light cache is your primary engine and set the secondary engine to none. Enable use camera path, make sure the mode is single frame. In the comment tab, enable active segment and set the very nth frame to every nth frame to 1. Okay, now let's up here enable save file. Let me go inside the render output folder for this lesson. Let me create a new folder and name it animated cubes or whatever you want. And let's save it out as PNG or whatever you like. Now let's hit the render and see what we're gonna have. As you can see, for each frame, V-Ray considers the entire camera path and calculates the light cache for the entire camera path. And because the mode is set to single frame, the light cache is being built for each and every frame separately. Now, if we didn't have those animated cubes, we could set the mode to fly through and it would have been a lot easier. Now, having use camera path enabled wouldn't entirely remove every single artifacts and flickering. It helps to reduce the overall flickering, but to get flicker-free animations, you need to increase your light cache settings. In this case, we actually didn't do that. We just have use camera path turned on, and we'll see how it affects our final result and animation. Now let me stop the render, and I can show you the final animations. Now, from the rendering menu, click on Compare Media in Ramp Layer. Now let's load the frames and wait a bit. Now, if I go frame by frame, you can see we still have some flickering, but it would have been a lot worse if the render was done without use camera path enabled. Actually, I have another render in which use camera path was off. Let's load that render in channel B. Now let me change the frame rate to 10 and play the animation. As you can see, the flickering is a lot worse in this animation. Take a look at the top of this table, for example, and every corner, and as you can see, we get tons of flickering. But in channel A, which is the render with camera path on, the flickering is a lot less compared to channel B. Okay, now let's close the ramp layer, clear the current image from the frame buffer. In the render settings and comment tab, make sure single is active as your time output. Also disable save file. In the GI tab, let's make sure use camera path is disabled for now. Also, let me hide these cubes. Okay, now let's talk about filters. Like Irradiance map in light cache, the samples will be created for some points in the scene. For the points without any light cache samples, we need to interpolate and average the samples that are around it to get the GI solution for that particular point, right? So that's when the filter parameters comes into play. We have three filters: none, nearest, and fixed. When set to none, no filtering or interpolation is done, and the value of the closest sample to the point in question will be used for that point. It is fast, but it can give some artifacts near the detailed areas. Next, we have nearest, and it uses the closest samples to the point in question and averages their value. And the number of these close samples is being controlled by interpolation samples down here. And it's better to use this one if light cache is used as secondary engine, which is most of the time. Finally, we have fixed. In this mode, the value for all the samples that fall into a certain distance from the point in question will be averaged and used as the value for that point. And that distance or size is controlled by filter size down here. It gives you smoother results compared to nearest, and this filter is preferable if you use light cache as your primary engine, which is rare. Now let's take a look at three renders with these three filters and see how they look. In the first render, the filter is set to none. The second one is nearest, and the third one is fixed. Obviously, from none to fixed, we get smoother renders. Also, if you increase the interpolation samples for the nearest method or the filter size for the fixed method, you would have smoother but less detailed renders. Now let me change the filter type to nearest again. Next, we have pre-filter, which is another type of filtering that is happening before the render, unlike the main filter that's happening during the render. And it kind of works on individual samples and makes sure that they are averaged properly, and the higher the number, the blurrier the final result and less detailed it will be. Now let me show you a few renders with different pre-filter values. As I go from 2 to 100, you can notice a slight change. We lose a bit details each time, and the overall result gets blurrier. Now let me set the render that has pre-filter of 2 as my A channel or A side, and pre-filter of 100 as my B. And we clearly have more detail on the left side, which is the A channel, but the result is blurrier and less noisy in the B side with pre-filter set to 100. Okay, let's set the pre-filter back to 20. Next, we have use for glossy rays. If enabled, the light cache algorithm will be used to compute glossy reflections and refractions in our materials. When we discuss materials, we'll be getting back to this option and demonstrate how it affects your material. Also, when you have this option enabled, it's recommended to have retrace also enabled. Otherwise, the light cache samples will be visible in the glossy surfaces. Next, we have store direct light, which is very important when you use light cache as a primary engine, and less important if light cache is your secondary engine. When this option enabled, light cache will be storing and interpolating the direct lighting also. Now in the frame buffer, in the first render, light cache is the primary and only GI engine, and store direct light is on. As you can see, the direct light is very blurry, and if I go to my lighting path here, you can see there is no information here. In the second render, store direct light is off. We get our sharp lighting back, and as you can see in the lighting path, we get the direct lighting the way we expect. So if light cache is your primary engine, you should disable store direct light. And if it is your secondary engine, you can turn it on because we get our sharp lighting from the primary engine in that case, which is Irradiance Map or Brute Force normally. In the next two renders, I had Irradiance Map as my primary engine and light cache as my secondary engine. In the first render, store direct light is on, and in the next one it's off. And it's really hard to see any noticeable difference between the two renders. Let's make sure store direct light is on and light cache is our primary engine. Next, we have bounces, which we discussed at the beginning of this lesson, and that is the number of GI bounces. And as I mentioned, this is a limit here, and light cache probably wouldn't use all these bounds, but the more bounce usually means more accurate and brighter renders. Let's see a few renders with different number for bounces. In the first one, bounces was set to 1. The next one is 2, and it clearly is brighter compared to the previous one. The next one is 3, 4, 5. And as you can see, each time the scene gets a little brighter because we allow the rays to bounce more. The next one is 10, and it's barely brighter compared to 5. The next one is 20, and the final one is 100. And as we increase the bounce number in the smaller numbers like 1 and 2 and 3, we can clearly see a difference. But here I can't see any difference between 10 and 100 bounce, for example, simply because after a certain point those rays wouldn't have enough energy to contribute anything. Also, Viri does not use all that 100 bounce. So that's why the difference is so small in the higher numbers. Let's make sure the bounce is set to 100. Finally, we have light cache modes. Single frame and from file are exactly like their Irradiance Map counterparts. In case of from file, the pre-filter calculation is not saved with the file. So if you load the light cache file, you need to adjust your pre-filter parameter before the final render. Next, we have fly through. If the camera is the only thing with animation in the scene, you need to use this mode. In this mode, the light cache for the entire animation is calculated in the first frame, and that same light cache will be used for the subsequent frames. Next, we have progressive path tracing, and right now it's more for legacy purposes, honestly, as there is a better way to achieve similar results, and that is the progressive image sampler that we're going to talk about it in the next section. The way progressive path tracing works is in this mode, light cache will be used to compute the final image progressively. So we'll have the entire solution just by using light cache. Let me just increase the subdiff to something like 5000 and start the render. You need to increase the subdiff number to get a fairly clean render when using progressive path tracing. What you see is actually the final image being progressively refined using light cache, and if we wait a bit, the image will get cleaner by time. Okay, let me stop the render here. As we used light cache in our complex scene in conjunction with brute force and Irradiance Map in our previous lessons, I'm going to skip that part. Another GI engine that we have is Photon Map, and Light Cache is derived from it and improves Photon Map in every single way. So I wouldn't explain Photon Map here because the Light Cache completely replaces it and improves upon it. Finally, let's sum up the strengths and weaknesses very quickly of Light Cache. First, it's very fast and gives excellent results as secondary engine. But it's not adaptive like Irradiance Map, and Light Cache is computed at a fixed resolution. It has some issues with bump maps. Also, when we have motion blur enabled in our camera, we can get some inaccuracy in our renders. So that's about Light Cache, and I will see you in the next lesson. In this lesson, we discuss general global illumination settings in the global illumination rollout. This is the same scene from the lighting section when we were discussing Skylight Portal and IES lights. If I go to my render settings in the V-Ray tab and global switches rollout, as you can see, I have override material enabled, but I have excluded the chair, the lamp, and the curtains from the override. Also, I have two hidden spheres here. One of them is this reflective sphere, which has a reflective material applied to, and the other one is this refractive sphere, which has a transparent refractive material applied to. We'll be using them when the time comes. These spheres are also excluded from the override material. Now let me show you a render of the scene with these current settings. So that is what we have right now. Let's get started with the parameters. In the GI tab and global illumination rollout, you can find some general settings that control different GI related things. Make sure the interface is set to expert so we can see all the options. First, we can enable and disable GI. Next, we can define our primary and secondary GI engines, obviously. Then we have two separate multipliers for the primary and secondary engines, and they determine the amount each one of these engines contribute to the overall illumination of the scene. The default of one is the physically accurate one, but you can adjust these multipliers if need be, which is not that often. Now, if I set the multiplier of my secondary engine to 0.5 and show you the resulting render, you can see the overall illumination gets darker compared to our previous render, and that might be what you want. But in most cases, as I mentioned, you need to leave these multipliers to 1 so you would get a physically accurate solution. Okay, let's set the secondary multiplier back to 1. Next, we have refractive and reflective GI caustics. When refractive GI caustics is enabled, indirect lighting can pass through the transparent or refractive objects and cause the caustics effect. Now, let me unhide this refractive sphere, which, as I mentioned, is transparent and has a transparent and refractive material applied to. In the first render, refractive GI caustics is disabled, and in the next render it's enabled, and you can clearly see the caustics effect caused by the transparent sphere. Now remember that this is an indirect caustics, and to get direct caustics we need to enable it from the caustics rollout down here. We'll be covering that later on. Next, we have reflective GI caustics, which if enabled allows the indirect light to reflect from the reflective surfaces, but unlike the refractive GI caustics, it's not contributing that much to the scene, so you can turn it off safely in most cases. In the scene, let's go ahead and hide the refractive sphere and unhide the reflective sphere. Now let me show you two renders with reflective caustics off and on. In the first one it's disabled, and in the next one it's enabled. I can barely see any difference. If I zoom in these kind of shadowy areas, you can see the enabled one is ever so slightly brighter, but really not that much. Now let's make sure reflective GI caustics is off. Next, we have saturation, which controls the color saturation in our GI solution. 1 is the normal value, 0 means no color, and anything more than 1 will result in more saturated colors. Now let's go over a few renders. In the first render, the saturation is set to 0. Also, I have just rendered the left side in the image, so we can compare it easily with the normal saturation on the right side, and also to save some time. When the saturation is set to 0, you can see we have absolutely no color coming from the GI solution, only shades of gray. When the saturation is set to 1, we have a normal render, and when set to 2, the saturation is twice and we get more saturated colors from the GI solution. Let's make sure the saturation is set to 1 again. Next we have contrast, which controls the overall contrast in our GI solution. Values less than 1 will make the GI to look more washed out, and values more than 1 will increase the contrast in GI. We have contrast base, which is the base for the contrast boost, and it determines the unchanged GI value based on which the contrast alters. Now let's go through some renders, and in these ones I also only rendered the left side. In the first render, the contrast is 0 and we get an absolutely uniform GI solution. If I go to the GI path, you can see that a bit better. Then the contrast was set to 1 and 2. And now, as you can notice, we have a lot more contrast. Let's set the contrast back to 1. Next we have ambient occlusion, and if we enable it, we will be adding an ambient occlusion effect to the overall GI solution. Basically, ambient occlusion is a black and white map where the corners and closed surfaces are black and the flat areas are white. Now imagine multiplying that map over the image, so the corners and detailed areas are going to get darker. Now let's enable ambient occlusion. Here first we have the value that controls the amount of ambient occlusion, so let me show you a few renders with different ambient occlusion values. In the first one, ambient occlusion is off, and in the next one it is set to 0.8, which is the default value, and you can clearly see those darker details and corners. And in the next one it is set to 2, and now it's a lot more obvious and exaggerated. Now in the next render I set the ambient occlusion value to 0.2, and as you can see it adds a lot more detail, but it's not unrealistic like the previous ones with the 0.8 or 2. And I usually don't use ambient occlusion, but if I happen to use it, I try to keep the value very low, because I think sometimes 0.2, 0.3 adds a lot, but without any negative effect on the realism of your image. Next we have radius, which is the radius of the ambient occlusion. Here I have another render with the ambient occlusion set to 2 and radius set to 50. And as you can see, compared to this render with the value of 2 and radius of 10, the effect is a lot more spread. And the subdiv parameter, which controls the quality of the effect, and higher number result in less noise in the final render. So that's about general GI settings, and I will see you in the next lesson. In this lesson, we'll be tackling an issue of paramount importance, which is rendering animations with moving objects in V-Ray. If you have ever rendered any sort of object animations in V-Ray, you know that having a flicker-free animation is really hard to achieve and really time-consuming. Usually, if you don't consider the right steps to render your animation, your final result will be an absolute mess, and you would notice flickering all over the place in your render. In this lesson, we learned the right approach for rendering animations with moving objects in V-Ray using Irradiance Map and Light Cache. We're going to be working with this scene, and if I hit play, we have this animation going on. I intend to work with just a chunk of this animation from frame 120 to 200, but if you want, you can experience with the first part of the animation too. So let me open up the time configuration window and change the start time to 120 and press OK. Let's open up our render setting. In the Common tab, make sure time output is set to single for now. And in the GI tab, set the irradiance map as primary engine and light cache as secondary engine. And let me use medium as the irradiance map preset. Also in the render elements tab, let's add global illumination and lighting passes. Without changing anything else, let's render the scene and see what we have. As you can see in the render named 01, we have visible splotches, and the first step to get flicker-free animation is to make sure that you have almost perfect GI solution on your individual frame. So if your individual frames are having a very good GI solution, your chances of getting flicker-free animations are much higher. But if the individual frames suck, there is no chance you have a presentable final animation. Also, if I go to the GI pass here, you can see the problem a bit better. Our GI solution is not acceptable at the time being. Now, in the lighting pass, we have some visible noise, but we'll be utilizing very denoiser to clear these high frequency noises later on. Back to our render settings and GI tab. The easiest way to get safe, perfect, and flicker-free animation is to use brute force, at least as your primary engine. If we set brute force as our primary engine and secondary engine, and then increase the subdivision to get the noise level to a minimum, and then render your scene, there would be nothing else to change. You're define where you want to save your final image and render the scene. To speed up the render in this situation, you can change the secondary engine to light cache and increase the light cache settings a bit. Using brute force will give you a perfect flicker-free animation. The problem, as you know, would be the rendering time. If I render my scene with brute force as my primary engine and light cache as my secondary engine, and render my scene, the result would be render 02. This render took 13 minutes, which is 10 times more than our previous render, which was just 3 minutes. But absolutely no splotches whatsoever. We might need to increase our brute force subdivision to decrease the overall noise, but generally you are guaranteed to get a flicker-free animation if you render all the frames using brute force. Now, in this case, we intend to render about 80 frames from 120 to 200. 30 minutes per frame is almost 2,400 minutes or 40 hours. That's a lot. For most of us, that's not a viable option. So in the render settings, let's set the irradiance map as the primary engine and light cache as the secondary engine. Now what we need to do is to crank up our GI settings until we get a clear GI solution. And when dealing with the animation, you need to really go the extra mile and make sure it is as good as it can get within a reasonable time frame, obviously. For this particular scene, I'm going to change the irradiance map preset to high animation and set the irradiance map subdivs to 90 and interpolation samples to 25. Obviously, I just didn't use these numbers from nowhere. I've experienced the scene, I have worked with the scene, I've tried different numbers, and I realized that 90 and 25 would possibly give me a very good result. So you need to go through the steps as we discussed in the irradiance map lesson, for example. In the light cache rollout, set the subdivs to something like 1200 or even more and retrace threshold to 8. As I have discussed these parameters in details, I won't be explaining them again here. If you have any problem understanding these parameters, please refer back to the previous lessons. Now, if I render the scene with the current settings, the result would be image 03, and if I compare it to our first render, you can see the quality has improved significantly, and the render time is only 5 minutes and 30 seconds. I mean, it really depends on your taste and what you consider good and acceptable. In this case, I would imagine an untrained eyes can't see any splotches in the scene. Now, me and you, we are working with this stuff. We know what is splotch and what is flickering, so we might be able to still find some splotches here and there, but someone who hasn't been dealing with this stuff, I imagine, cannot find any splotches or any problem with the scene. Now, obviously, you are seeing this through the recording and the Make sure to check out the history in the frame buffer on your own, because this video will go through some compressing to be able to kind of make it downloadable. You really need to check the original files in your history folder of the scene. Now, the next step would be to save out the GI solution for all the frames. To do that, change the irradiance map mode to animation prepass. Now, V-Ray asks you where do you want to save the GI solution for all the frames. Let's go to the render output folder of this lesson. Let's create a new folder and name it irradiance map and go inside it and set the file name to box or whatever you want and press save. Also, if in your scene, in addition to object animation, you also have a camera animation, please enable use camera path option both in the irradiance map and light cache. In the comment tab, change the time output to range, and even though we are only rendering our animation from frame 120 to 200, but I'm gonna set the range from 118 to 202. So basically we are having a 2-frame margin on each side, and the reason being is the interpolation frame number in our irradiance map settings. Because imagine if we render frame 120, because the interpolation frame is set to 2, we would need the irradiance map for 2 frames before 120 and 2 frames after it, and the same thing for frame 200. So that's why we start from frame 118 and end it at 202, even though the final render will be from 120 to 200. Also, in the render elements, let's delete all the elements that we have. It's not necessary because in the animation prepass mode, V-Ray won't render the final image and only GI will be calculated, but I tend to make sure I have no render elements in this step. Now you can press the render button and V-Ray calculates the irradiance map and light cache for all the frames in the animation and creates one separate map for each frame. After the GI is calculated for each frame, V-Ray will start GI calculation for the next frame and skips rendering the final image. As you will see, after the first frame is finished, we start calculating the GI solution for the next frame immediately. Now, we wait, and after the GI calculation is finished for all the frames, I'll be back. Now, if I open up the irradiance map folder that we just saved our irradiance map to, you can see we have generated an irradiance map for each frame. The interesting thing is these maps also contain the light cache solution, so we don't have to calculate our light cache separately. In the GI tab, what we can do now is to set our secondary engine to none because all the light cache samples are saved in our irradiance map. In the irradiance map rollout, change the mode to animation rendering. Now you need to select the first irradiance map in the sequence and press open. For each frame, V-Ray will use the proper irradiance map. So if we render frame 142, the map for this frame will be loaded. In the comment tab, let's change the time output to active segment. In the render elements tab, let's add denoiser, lighting, and global illumination. Also, let's set the denoiser preset to mild. Now you are ready to start your final render. If you get back to the Irradiance map rollout, now that we have set the mode to animation rendering, interpolation frames parameter becomes available. And by default it's set to 2. I'll be getting back to this parameter and show you how disregarding it might lead to severe flickering in your final render, but 2 is normally good enough to give us a flicker-free render. There are several ways to save out the final image. You can use save file up here, but I usually tend to use frame buffer rollout under V-Ray tab to save out my final render. We will be discussing all of these parameters later on, but for now let's enable V-Ray raw image file. Click on this browse button here. Let's go to the final render folder in the render output folder for this lesson. Set the OpenEXR as the output format and change the file name to box and click save and start the render. As you can see, we skip irradiance map and light cache calculation because we already have those information, and start the rendering of the final image. Now you might think you are going to get faster render time per frame because you skip irradiance map and light cache calculation. Because we are rendering an animation and interpolation frame is set to 2 and we are blending between 5 frames at each frame, the render time is not going to decrease that much, and based on the material that you have in the scene, it might actually increase, and it might increase significantly, sometimes to 4 to 5 times per frame before setting the mode to animation rendering compared to the when the mode was set to single frame. So if, for example, the mode set to single frame and you would get a render time of maybe 5 minutes per frame, if you have very complex materials in the scene, when you set the mode to animation rendering and interpolation frame is set, for example, 2, you might get to 20 minutes per frame or something like that. So you might increase your render time significantly based on your scene. Now in this case, it doesn't change that much because I don't have any complex materials in the scene. Now you just have to wait, and when the render is finished, I'll be back to take a look at the final results. Here we are inside After Effects to take a look at the final render. Let's double click in the project panel, select the first EXR file, make sure OpenEXR sequence is enabled and click import. Now let me create a new composition based on this sequence. Change the project to a 16-bit project and the working space to sRGB and enable linearize working space. And press OK. Now we are in the right color space. Also, let's right click on the footage, from interpret footage, select main, set the alpha to ignore and press OK. Now you can press 0 on your keyboard and wait a few seconds for the preview to be ready. So here is our perfect flicker-free animation, and as you can see, the result is amazing. I mean, we still have some small noise to get rid of that can be solved simply by using V-Ray denoiser pass. We already have V-Ray denoiser pass saved in our final render. So let me stop the playback here. From Effects and Presets panel, let's search for Extractor and apply it to the render. Click on this empty space and from Layers, select V-Ray denoiser. Now let's press 0 again and wait for the new preview. So here is our noise-free, flicker-free render. And if this bending that you see on the wall is from After Effects preview and not from the render itself, and if you render out the sequence to a video format, you won't see that problem anymore. Now back to 3ds Max. Let me open up the RAM player and open up the sequence here. Make sure the frame rate is set to 24. If you play the render, you can see we have a beautiful flicker free render and there is no bending on the walls. Okay, perfect. Now let me close the RAM player and discuss one last thing before wrapping up the lesson. Now what I want to discuss here is the effect of interpolation frames while you unflickering. In the frame buffer I have 3 sets of renders. In each set interpolation frames was set to 0, 1 and 2. I have just rendered this very small portion of the image around the main sphere to speed up the process. In the first set the interpolation frame was set to 0 and I have rendered frames 188, 189 and 190 in order. Let me go through these renders. You notice how the reflection on the sphere here is not constant throughout those 3 frames and we get very obvious flickering even in these 3 frames. Now imagine how it would look like in the entire animation. In the next set, interpolation frames was set to 1, and as I go through these renders, you can see the flickering is a lot less. And in the final set, interpolation frames was set to 2, and as you can see, flickering is completely gone. These renders are obviously taken after we have calculated the irradiance map and GI and have set the irradiance map mode to animation rendering. That's where the interpolation frames comes to play. In fact, let me just load an entire render with interpolation frame set to 0 and you will notice severe flickering that it causes. Let me open up the RAM player. I have another folder called with reflections, and in this render the spheres are having a reflective glossy material and interpolation frame was set to 0. Let me load them in the player here. Now I want you to focus on the reflections on this big sphere. As you can see, it's severely flickering, and I can also go frame by frame so you can notice the flickering even better. So the moral here is to make sure your interpolation frame number is high enough to prevent any flickering. Okay, so that's about rendering flicker-free animations in V-Ray. I know it seems very complicated and doing this step and doing that step, but in fact it's not like that at all. After a while it becomes your second nature. You just watch these lessons a few times if you find the content to be a bit difficult, but I promise you it's not difficult. Just watch it again and you can see how easy it is and how quick it can be done, because I'm kind of talking about this stuff and make sure you understand everything. That's why it takes so much to set up. In fact, it takes 30 seconds to set up everything, besides the renders, but it's going to be very fast and very easy. Just try to watch the lessons a few times if you have any problem. So perfect. See you in the next lesson.